Right, can you see a slide on screen? All right, thanks. Right, yesterday we have started discussing about the concept of generation and recombination. Okay, so generation is basically the process where we generate carriers, or if you want to sketch the process in terms of the Venn diagram, so that means excitation of carriers from the valence band into the conduction band. Okay. On the other hand, the reverse process is called recombination, where the excited electrons in the conduction band drops into the valence band and recombine with the hole. Okay, and we learned that at thermal equilibrium, the rate of generation is equal to the rate of recombination, or R equals to G. Okay, or R minus G equals to 0. And the R can be represented or can be calculated in terms of this equation, using this equation, beta times naught, N naught times P naught, where the beta is the constant. Okay, so we've also discussed about methods that we can use in order to generate excess carriers. So when we talk about excess carriers, so that means we are generating new carriers on top of the carriers which already existed at thermal equilibrium condition. Okay, so that's why the notation of naught becomes very important. Naught, N naught, P naught will become very important in order for us to differentiate the concentration of carriers at thermal equilibrium versus the concentration of carriers under new condition where we have excess carriers. Okay, pardon the sound, ada dekat saya kat office sekarang, ada orang tengah innovation. Right, so we can generate excess carriers by a couple of methods. Firstly, by optical excitation, as an example. So where you shine light on your semiconductor and you can generate new excess carriers in the semiconductor material. So you can also use electron bombardment, for example, by bombarding high energy electrons on your semiconductor material in order to generate excess carriers. And you can also use doping, the concept that we've learned before, in order to introduce carriers into your semiconductor material. And this is also called carrier injection. Okay, so for your information, when we talk about carrier injection, you can also say that carrier injection can occur by any of these three processes, not only limited to doping process. Okay, so when you're exciting new carriers optically, you can also say that as carrier injection by optical excitation, or you can also say that you are injecting carriers into your semiconductor by electron bombardment. You can also say by doping, right? So it's not only limited to doping process. So we've stopped on this page yesterday where we discussed the change in the carrier concentration when you have excess carriers. So on this page, you can see that excess carriers, as an example, is explained in terms of N-type semiconductor, where we expect more electrons to be generated into the silicon, and therefore that will skew the distribution of NP to be more than NS squared, right? So, and we have also discussed the concept of steady state of system equilibrium, where we learned that if you apply external agents on the system, on the material, for example, by light, electric field, and whatnot, but constant with time, we can say that your semiconductor material is in steady state condition, right? So let's just recap this this discussion that we stopped yesterday. For example, if you are creating excess carriers into the system of N-type semiconductor, which is earlier on doped at 1017 as an example. You can see the explanation on the next page as well. So let's just do some, assuming you start off with an N-type silicon doped at 10 to the 17. So that means your N naught is 10 to the 17, isn't it? 10 to the 17. Okay, 10 to the 17. If you are generating excess carriers, which can be represented as delta N, which also equals to delta P, because we need to break a bond in order to generate new carriers. Say your excess carriers is around 10 to the 12. Okay, so let's have a look at these two equations. What happened at the two equations here? So bear in mind that you are working on N-type silicon. So your delta N is 10 to the 12 and your N naught is 10 to the 17. So let's look at the first one. So what happens to the value of N? So your N here is your new carriers, which is the summation of your excess carriers plus your original carriers, right? So delta N plus N naught, and that is almost equal to ND, because when you add 10 to the 12 to the 10 to the 17, you essentially get 10 to the 17, isn't it? So that's why your N here can be approximated to ND, because you barely change the carrier concentration of the majority carriers, right? On the other hand, so remember that is the majority carriers, electrons. So that's why you have to really understand this concept. So what happens then to the minority carriers? Minority carriers here is given by 10 to the 12 for the delta P plus, what is the P naught value here in this case? What is the value of P naught for this case? Silicon Ni times 10 to the 10, right? Good. So your P naught is 10 to the 3. So what do you get? So what is the value of your P? What do we get? 10 to the 12 plus 10 to the 3. So what's the result? 10 to the 12, isn't it? 10 to the 12. So 10 to the 3 becomes very, very small in comparison to 10 to the 12. And therefore, your P is equal to 10 to the 12, or it can be approximated to 10 to the 12, which is essentially equal to your delta P. Okay, so now you can say that when you have 10 to the 12 of excess carriers added to the existing 10 to the 17 of majority carriers and 10 to the 3 of minority carriers, the excess carriers barely change the majority carriers. Okay, the majority carriers remains 10 to the 17. But the excess carriers in this case does change the minority carriers. So minority carriers changes from 10 to the 3 for the P naught and becomes 10 to the 12, which essentially is the value of delta P or delta N, right? Okay. So this is the very same example, but slightly different with slightly different magnitude. The process of introducing extra carriers is referred to as carrier injection, right? So you're adding carriers into the system, adding carriers into the lattice, adding carriers into the silicon or whatever your silicon material is. When light is absorbed, carriers are created. So now we're talking about optical excitation as one of the examples that we can use in order to generate excess carriers. But you can also use other techniques in order to induce excess carriers. So introduce excess carriers into the material, right? So delta n, we know that delta n is equal to delta p, because to be able to create a free electron, you have to break a bond, and that equals to free hole as well. And n is given by n naught plus delta n, and p is given by p naught plus delta p, as we discussed in the previous page. So the magnitude of the excess carrier delta n equals to delta p determines the injection level. So your injection level may vary from a very low level up to a very high level. So we discussed on the 10 to the 12 as only one example of, or one possibility, if you like, of the injection level. So the injection level can be 10 to 15, 16, 17, or it can even be lower than 10 to the 12, depending on the excitation condition, right? And that is called carrier injection level, okay? Injection level. So that means you may have low injection level, you may also have a high injection level. For example, if ND is 10 to the 15, we discussed on the 10 to the 17, so ni sama aja, the very same thing. Therefore, N naught is equal to 10 to the 15, and P naught equals 10 to the 5. So we've been discussing about 10 to the 17, and therefore P naught is 10 to the 3. So if you're talking about P-type material, for example, then your Na will be equal to your P naught, and your N naught will then be equal to Ni squared over N naught, right? Or sorry, or over P naught. So that will give you your minority carriers. So that's why understanding the concept of majority carriers and minority carriers is very important in this case, because you need to calculate the majority and the minority accordingly, right? So if the sample was illuminated and your N, delta N, delta P equal to the 12, for example, then we go back to the very same discussion on the previous page, right? 10 to the 15 plus 10 to the 12 is equal to 10 to the 15 or close to. We can approximate your N to be equals to N naught, which means your excess carriers in this case barely changes your thermal equilibrium electron concentration, right? Because not here is the thermal equilibrium condition. That is why I keep stressing about the meaning of your subscript, not, right? So because you need to compare the excess carriers condition, thermal equilibrium condition, and the new condition, which is the summation of thermal equilibrium and your excess carriers, right? On the other hand, if you need to do the calculation for P, and that is given by 10 to the 5, which is the minority carrier concentration, the P naught plus delta P, so that can be approximated to 10 to the 12, which is essentially delta P. Okay, so as discussed on the previous page and on this page as well, you can see that if your injection level is way lower than your original concentration of the majority carriers, it barely changes. It wouldn't change the majority carriers, but it will only change the minority carriers, right? But that depends, of course, right? That depends. When excess carrier concentration is much less than majority carrier, that is when delta N is way lesser than the N naught. So in this case, we're talking about yeah, we're talking about 10 to the 12 versus 10 to the 15. Then your injection condition is called low level injection. Low level injection. Okay, when your excess carriers is way lesser than your majority carrier concentration. So on the other hand, if your majority carrier, if your excess carrier is close to your majority carrier concentration, and that will be called a high level injection. When excess carrier concentration is greater than the majority carrier or equal to, okay, which is the other extreme, the condition is referred to as high level injection. Okay, high level injection is a lot harder to analyze, right? But you may have this condition as well, depending on your excess carrier generation condition, right? So we have discussed about the concept of direct band gap and indirect band gap last time. Okay, remember? Can you recall what do we have on the left? The left one is indirect band gap or direct band gap, and why? Let's recap before we started discussing about absorption of light. What do we have on the left? Is this an indirect band gap semiconductor or direct band gap semiconductor? The one on the left. I give you about 10 seconds to think. Then you can unmute yourself. You can input your points, input your opinions in the chat box. 10 seconds. Let's recap on this. Right, let's hear from 10 seconds gone. Let's hear from Shazanani. What do we have on the left? Shazanani Firzana. What do we have on the left? Cuba tengok tu. Indirect band gap or direct band gap? Let's revise this concept that we learned before. Not sure? Okay, all right, that's fine. So let's discuss about this. Fatin, you have any idea, Fatin? What do we have on the left? Is it an indirect band gap semiconductor or direct band gap semiconductor?
Indirect semiconductor.
Okay, indirect. Kenapa, Fatin?
Because the EC and EV are not aligned.
EC and EV. Can you be a bit more specific? Which part of EC and EV is not aligned? Cuba tengok dekat sketch tu. It's not aligned, yes, correct. But which part, to be more specific?
For the EV is the maximum point, while for the EC is the minimum point.
Yes, good. Right, thank you. So it's not aligned in terms of its local maxima of your EV and local minima for your EC, right? So the moment you don't see them on the very same value in the K crystal momentum on the x-axis, so that means they are indirect, or it is an indirect band gap semiconductor, right? Good. So on the other hand, you can see on the right where your local minimum and your local maximum is aligned at the same value of x-axis, right? So let's recall, what are the examples of semiconductor materials on the left? What are the examples of semiconductor materials which have indirect band gap properties? Ni recall tajuk yang kita belajar awal dulu. Let's hear from Anis. Do you have any idea, Anis? Oh, Anis ada dua ni. Anis Syabirah, Anis Amira. Anis Amira, can you recall the examples? Anis, any idea? Any examples of materials from the left? Silicon. Can you be a bit more specific, Bala? Silicon, but remember last time when we talked about silicon, silicon itself can be divided into few parts, right? Few types. Which silicon, Bala? Crystalline or amorphous silicon? Remember last time we talked about, yep, crystalline silicon, isn't it? So crystalline silicon has an indirect band gap, whereas amorphous silicon has direct band gap. Okay, so if we talk about the properties on the left, then we're talking about crystalline silicon, we're talking about germanium, but on the right we have quite a number of examples, like gallium arsenide, cadmium telluride, gallium nitride, amorphous silicon, and many more, right? So when you talk about absorption of light, to be able to absorb the light, the valence band electron needs to be excited into the conduction band, right? Needs to be excited into conduction band. So that means you have to go up. So for example, if you talk about crystalline silicon on the left, so the transition need to be vertical transition, and also horizontal transition in order to get there. Okay, sampai ke local minimum, from local maximum to local minimum, and you need to have the same crystal momentum, the same value of crystal momentum to be able to allow the excitation to take place, right? So on the other hand, it's a lot easier to happen in a direct band gap because the momentum is already aligned. So you just have to have vertical transition of the valence band electrons into the conduction band, right? To be able to allow absorption to take place. So when you talk about light absorption, there are various examples or devices, for example, solar cells, photodetectors, and light sensors. So whatever devices that need to have light excitation in order to operate, okay, macam solar cell, sensor, light sensor, and everything, right? And you need to have incoming light in order to excite the valence band electrons, right? So we've learned before that light consists of photons, and photon under their own energy, right? At different energy levels. So the photon flux within the material, we're going to look into this a little bit detail later on. Within the material here means dalam your silicon, for example, crystalline silicon, right? The photon flux, if you want to see the distribution or the profile of the flux within your semiconductor material. So for example, if I take this silicon wafer, so just take this silicon, I have silicon solar cell with me as an example to show this. Okay, as I showed before, this is a silicon solar cell, about 5-inch white. So if you talk about the flux that's coming into the silicon, they were talking about that cross section. So that means the light's coming, the photons coming from the top, and then it's going to penetrate into this silicon. This silicon thickness is roughly about 180 micron, and that's like twice of your hair thickness. Kalau cabut satu, you letak 2 helai rambut. So the thickness of those 2 hair is about the thickness of this wafer. Okay, so we want to talk about the flux that's coming into the silicon. Okay, maksudnya yang saya sketch kat sini ni, is actually flux coming into silicon, and this silicon thickness is about 180 micron, or twice of our hair thickness, pretty much. Lebih kurang, So you want to know the flux inside at certain point, at certain depth within this silicon, crystalline silicon wafer, right? And the flux, the equation is given by this. Fx equals to F naught. F naught is the intensity of the flux right at the center of the surface, right at the surface. So naught here means the surface, So that means X equals 0 or depth equals 0. So as you go into the crystalline silicon, as you go into the X, then it's going deeper and deeper, right? And that's given by F naught exponential of negative alpha. Alpha is the absorption coefficient of this material. So whether it's crystalline silicon or amorphous silicon, gallium nitride, zinc oxide, whatever, doesn't matter. So each material has its own absorption coefficient. Right? Absorption coefficient simply tells you how efficient is the absorption of light by this particular material, right? So you will see the comparison later on. And X here is the depth into crystalline silicon or cadmium telluride or gallium arsenide, gallium nitride, whatever, the X, okay, into silicon. And it starts from the surface. The surface is where the X is 0, and then the X increases as you go into the volume of your semiconductor material. So that's the flux. The photo generation rate. photo generation here simply means the generation process yang kita dah belajar tadi G. But then why is it called photo generation? Because the generation process is happening by photon illumination. That's why we call it photo, due to the photon, due to the light, which causes generation of carriers. That's why we call it photo generation. Photon help to generate the carriers within your semiconductor material. And the photo generation rate is given by Gx, okay, Gx, which equals to alpha. Alpha is simply the absorption coefficient times the flux. The flux is the flux that we discussed in the previous equation, right? F naught exponential negative of alpha, absorption coefficient, times the depth into the material. Okay, so it's still abstract at this point. Let me just show you something on the next page. Right, we'll go to the link shortly. Yeah, so when you have incident photons on the surface, okay, bila you ada incident photon, bila you ada light hitting on any surfaces in the world, okay, tak kira lah tingkap ke, silicon ke, whiteboard ke, baju ke, langsir ke, buku ke, meja ke, doesn't matter, any surface. So there'll be few things happening to the light, right? So bila you have any light incident on this surface, it doesn't matter it's coming from whatever angles, whether it's right angle, normal to the surface, perpendicular, at whatever angle, perhaps a low angle, high angle, it doesn't matter. So when you have this incident light coming to your silicon, for example, it can also be some other semiconductor materials, the light will either be reflected, you're going to have some reflection, right? So whatever that's not reflected will be going into the material. Again, the material can be anything. So some portion of the light will be absorbed. Okay, some portion already reflected away off the material upon incidence, and then the remaining will be penetrating into the X, into the depth of the material, and then some portion of the light, some portion of the photons will be absorbed, right? So the photons that are not absorbed will be transmitted at the back. Whether you can see that or you cannot see that, right? So that means if I have this very silicon, I show you this cross section. So this is my incoming photons, for example. So it's coming at some angle. So this is cross section. So some will be reflected off the surface upon the first incidence. So anyone has any idea why is it getting reflected off the surface? Any idea from your previous optics knowledge? Second year course. Why is it reflected? Why you have reflection? Why you have reflection from any surface? Any idea? What gives reflection? What leads to reflections? Why do you see things? Because you see reflection, because of reflection, right? Why do you have reflection? Anyone? Kenapa ada reflection? Why do you see blue? Because of reflection. But why do you have reflection? Any idea from the optics knowledge? Kenapa kita dapat reflection? Any idea that you can recall from the previous course? We're going to go to the link shortly. Because it's opaque? Yes, but it's not very... It's opaque, it's blocking the light. But why reflection? Okay. Travel through different material. Yes, it's traveling through different material, therefore you have reflection. But what dictates the reflection? Yeah, total internal reflection is one of the examples of reflection that you may have. But why do you have reflection? Let me just narrow down the answer from Zul. Travel through different material, correct? But what is the parameter of the materials that kenapa kalau they travel through different material, you're gonna have reflection? Critical angle, close, one of the parameters that we need to know in order to talk about reflection. Apa parameter? Apa? That's close, Fatul. Index. I'm looking for index number, but what exactly? What was that? That's not quite there. The word is index, but exactly what is it? Kenapa ada reflection? Zul said, yeah, exactly. Not reflection index, close. Ubah sikit. Bukan indeks pantulan. Indeks apa tu? Satu lagi. Biasan ke? What is N? Baca tak dulu N. What is this N? Refractive index, right? Refractive index. Okay, let's recap kita punya optics knowledge. Sebab kita nak belajar generation ni. So this is only one aspect of generation, which is by light. We have not talked about electron bombardment. We have not talked about doping. Banyak lagi cara. So let's recall. What is the refractive index of the air? Ni sekarang ni saya punya office ni air. What is the refractive index? What's the N value of the air? Try search. Try Google search. Right? Good. Bala. N equals 1. Good. Fada. N equals 1. Try to search for refractive index of crystalline silicon. Cuba search. I give you about 10 to 15 seconds. Search refractive index of silicon or crystalline silicon to be more accurate. Lepas you faham konsep ni, you can digest all the reflections that you have in this world. Anyone found any numbers from the internet? What's the magic number of silicon? Anyone found anything? All right, Bala 3.8. Any other numbers? Well, it's wavelength dependent, right? It depends on where do you see the figures, right? So it's really dependent on the wavelength. If you see at 400, then it's going to be a bit different to the values that you get from 800, for example. But it's roughly around 3.8, 3.9 for that, right, in the visible region. So that means when you're talking about crystalline silicon, we have not discussed about some other materials yet, but the principle remains the same. So the photons are coming from the air, N equals to 1, and then it hits the surface of crystalline silicon, N equals to 3.9. So the moment it hits different media with different refractive indices, you are going to have reflection. Okay, that is the cause of reflection. Okay, so you can always check this out. You can always check Fresnel reflection, Fresnel R reflection R, N1 minus N2, N1 plus N2 squared. Okay. Can you try? I wanted to try press your calculators. What if try to plug in your N1 as 1 air. N1 is your air. N2 is your crystalline silicon. Right. You can use the value given by Bala, let's say crystalline silicon 3.9. Can you plug in the values there and what do you get for reflection? 1 minus 3.9, 1 over 1 plus 3.9 squared, all. What do you get? I'll give you 5 to 10 seconds to plug in those numbers. Anyone got anything? Can you share in the chat box? Cool, 0.35, right? Fada, any numbers? Any other numbers? Good. That's about 35. That's about 0.35 to 0.4, depending on the refractive index that you pick. But that's close to, that's about, if you convert this, Fada and all, you can convert that 0.35 to percentage, and that will give you about 35% to 40%. So that means if I take my silicon, hold on. I have my bare silicon here. Ada bare silicon. Tadi tu silicon yang ada coating. So this coating here, if you talk about optics, this coating is actually silicon nitride to reduce reflection from the front surface, to make it not shiny. It was originally shiny, as in this silicon wafer. You can see some reflection, right? At least from my camera. So you can see some reflection. You can see pictures kan, nampak gambar kan. So that means reflection is there. On the other hand, on the blue silicon solar cells now, you couldn't see any reflection. You can just see blue. So that means the reflection level has been reduced. So on this silicon, the original silicon, crystalline silicon wafer, monocrystalline, a single crystal, the reflection level here that you are seeing here, if you measure, so that's roughly about 35% to 40%. Okay, so apa is 35 to 40%? That's driven by this, dictated by this Fresnel equation, Fresnel reflection. 1 minus 3.9 over 1 plus 3.9 squared, you're going to get about 35 to 40%. So the reflection level that you're seeing here is actually 35 to 40%. Kalau you measure. Kalau tak measure, then you nampak, oh, it's reflective, nampak muka, macam cermin, like that, just qualitative. But then if you measure, you're going to get somewhere about 35 to 40%. Okay, so that will dictate the level of reflection that you have here. Right, the same goes to your mirror. Kalau you balik tengok cermin, you try to see what codes, what makes the mirror. Layer apa yang ada kat atas cermin tu? Kenapa you get to see yourself, right? You get to see yourself at different angles and stuff. So what is the reflection level there that you're supposed to get for a typical mirror that you used to comb hair, pakai tudung dan sebagainya kan? So those are all optics, right? So clear. So the moment you know your media from media 1 to media 2, you can then plug into this Fresnel equation and you can tell right away the reflection level is such and such, just by knowing the refractive indices of the two media. And then some portion will be absorbed, and this depends on the incoming photon energy that's hitting your silicon, your gallium arsenide, whatever. If the photons have enough energy, they will have enough energy to excite the valence band electrons into the connection band. On the other hand, if they don't have enough energy, they will not be able to excite the valence band electrons into the connection band. Right? We're going to see that shortly in the link. And whatever that is not absorbed will be transmitted at the back. Okay. Kalau you can also use this concept RAT. If you combine them, R, and A and T, if you add them up, R plus A plus T, that will actually give you 100%. So that means 100% is the incoming light to your windows, to your silicon, to your whatever. So out of that 100%, some portion will be reflected, say 35%. So you're going to be left with about, what, 65%? So out of those 65%, perhaps say 40% will be absorbed, 25% will be transmitted at the back. Okay, you can use this very concept for your windows. Kalau you're imagining your windows is solar windows, maksudnya bila light masuk dalam, hit the window into the before it gets into the building, some portion will be reflected, and that depends on refractive indices and stuff that we just calculated, and then some portion will be absorbed in order to generate the electricity for the building, solar windows, because it is there for electricity generation, and then some portion will be getting into the building as your natural light. Okay, so the very same concept is actually applied as solar windows and some other opaque material. In fact, kalau you cakap tentang this opaque material, then there will always be some lights transmitted at the back, but you don't get to see them because they are all infrared component. Ada je light yang keluar kat belakang ni, but I don't get to see them because they are all infrared. They are not visible. Okay, they are not visible photons. So now let's finish off by looking at this, by going to this link to explain to you the concept better. Let me share the website so that you can appreciate the concept of light absorption for carrier generation. Stop sharing. Share already. Okay, can you please confirm if you can see the website on the screen? Yes. In case. All right, good. So all you have to do is go to this PV education. Well, I told you last time it's meant for solar cells in particular, but the concept that you're going to learn here basically semiconductors, right? Before it gets specifically on solar cells. So when you have your incident light or incident photons coming onto your silicon, onto your gallium arsenide, cadmium telluride, and whatnot, so the photons can be divided on into these three groups. Okay, there are tiga kategori je of the incident photons if you talk about light absorption. So case number one, let's see case number one. We're going to see some animation later on. Case number one is when EPH is less than EG. What does it mean? EPH is the energy of the incoming photons, which is less than the band gap, right? If you talk about crystalline silicon, then we're talking about the incoming photons having energy less than 1.12 electron volts. And in this case, the photons will not be able to excite valence band electrons into the conduction band because they can only interact very weakly with the semiconductor. What happens? Then the photon will just pass through at the back as if the silicon, the crystalline silicon, were transparent, as if. Maksudnya dia lalu je lah, tak boleh buat apa pun because the energy is not enough to knock the valence band electrons into the conduction band for excitation, right? Case number one. Case number two, when your EPH is equal to EG, right? So your EG is 1.12 electron volt in this case, so that means your incoming photons have energy of 1.12 electron volt exactly, which just have enough energy to create electron hole pairs, and these photons will be efficiently absorbed. Okay, when your photon EPH equals to EG will be efficiently absorbed, and that will cause optical excitation of the valence band electrons from the VB into the CB. So you're going to get your excitation because energy is just right. Okay, energy is just right. Case number two, right? Case number three is when your EPH is more than EG. Macam saya bagi example tu, nak cross the bridge, you have extra fuel and you can go further into Balik Pulau and so on, Fringy perhaps. Right, photons with energy much greater than the band gap are strongly absorbed. They'll be absorbed as well, but then they will cause excitation of the valence band electrons further up into the CB, not just right at the edge. They can be further up, right? And that will cause the electrons to quickly thermalize back to the CB edge, to the conduction band edge, right? So let's see these three examples in the animation before we finish off the class for today. And you can just come to this website and play for yourself. So the creation of electron hole pairs when illuminated with EPH or more than equals to EG or more than, right? Case number one. Let's see. EPH less than EG. So though that's the incoming photon, so there's no absorption because the EPH is less than EG. Light with energy less than the band gap is not absorbed and passes straight to the semiconductor. So as if it was transparent. So maknanya photon yang coming tu akan keluar kat belakang lah, transmitted, right? The P component will be there, but there will not be any absorption at all. The A will be zero. Reflection will of course be there because of the refractive indices difference. Next, EPH more than EG, case number three actually, right? So that will cause excitation, isn't it? High energy photon gives its energy to electron moving up into the conduction band further up, not just at the edge, leaving a hole in the valence band. So a hole will be left in the valence band. What will happen next is thermalization of both, right? Thermalization to the edge is called thermalization process. The excess energy is wasted. So maksudnya if you work on optical devices like solar cells or light sensors, so if you absorb the photons with energy more than the band gap, the extra energy will be wasted as heat. Okay, so those are actually opportunities for you to think of what else can be done with those wasted energy, right? Next, EPH just equal to EG, a photon with energy equal to the band gap is efficiently absorbed and there is no heat wasted, as excitation will take place from the conduction band, valence band edge to the conduction band edge, right? So then the photon will be absorbed and you're going to get excitation. Okay, so let's just recap. Out of these three scenarios, how many scenarios can cause light to be absorbed? How many scenarios out of these 3 scenarios causes light to be absorbed? Okay, 2, 2. Okay, right. 2 out of 3 causes light to be absorbed. Good. How many scenarios causes thermalization process? How many scenarios causes thermalization process? Right, just one. When your energy, the photon energy is more than the EG, right? So only one. Right, and the first one is obviously there's no absorption, right? Okay, good. So let me see what else do I have. I think I'll just stop here. So tomorrow we're going to continue with absorption coefficient, the alpha. So what is alpha? What does it mean? And then we're going to finish with generation and recombination hopefully tomorrow. Okay. So do you have any questions on today's class? Any question on light absorption, on the 3 scenarios, on the carrier injection level? Nope. All clear? Good. So 3 scenarios, huh? If you have incoming light, so there's only 3 scenarios. And you can always relate that to the A, parameters A tadi ya, parameter A. We talk about R plus A plus T equals 100, and 100 is the incoming photons, if you like, to the semiconductor material, and some portion will be reflected off the surface due to the difference in reflective indices between the 2 media, and whatever that is not reflected off first time, because there will be reflection second time, third time, many more total internal reflection. Tapi to simplify things, let's just assume that the first reflection is considered in this case. Sebab bila the light gets into the silicon, crystalline silicon, and then it gets back to the air, will there be any reflection anymore? Tadi kita tengok reflection of the surface upon entering silicon, right? How about upon leaving silicon? Will there be any reflection as well? What do you think? Based on the Fresnel reflection concept just now? Is there, will you still have any reflection at the back? Using the very same concept? Leaving silicon, photons leaving silicon at the back. Do you expect reflection at all? Anyone? No? When the photons leaving silicon at the back, imagine yourself as a photon. Kalau you nak keluar silicon kat belakang, do you encounter different refractive indices? Do you encounter a new media? Right? Do they have different refractive indices? Yes. Therefore, if you plug it into Fresnel reflection coefficient, Fresnel reflection equation, do you get any reflection value? Yes, right? So you are going to encounter different media which have different refractive indices, and if you plug in, you can replace silicon as N1 in that particular case, and the air at the back will be N2. So you are leaving silicon N1 into N2 air, so your silicon is 3.9, your air is 1, you just 3.9 minus 1, 3.9 plus 1 is squared, you still have, you're still going to get some level of reflection, isn't it? So that means, so that is another reflection that we've not considered in this particular case, just to simplify things. Tapi sebenarnya ada reflection kat belakang. So that's why you tend to get total reflection and stuff, Brewster's angle, all the stuff. Not to complicate things, but tapi akan ada reflection level at the back as well. Okay, all right. I hope that's clear for now. So let's continue tomorrow with absorption coefficient, absorption gap, and the rest of the materials. Right? Okay. So if there's no question, I'll see you tomorrow. Inshallah. Bye bye. Take care. Assalamualaikum.